Welcome everyone to the Global Noncommutative Geometry Seminar today. So our speaker is Damien Tegeddine from McGill University. So Damien is going to tell us about noncommutative geometry on the Berkovich line. So please, Damien.
Thank you, Cheng. Thank you, everyone, for being here and for the kind invitation. It's a pleasure for me to talk at this seminar. So, as written, I'm going to talk about non-commutative geometry on the Berkovich line. This is a joint work with Masoud Khalkhali from Western Ontario. And it's an ongoing work, so we've already submitted a paper on this, and probably more on the subject will come. So I'm going to start with a brief motivation on the subject, and then I'll describe the Berkovich line and how to construct sort of non-commutative geometries on this space. So let's start with a brief motivation. So the general philosophy here is that before studying a problem over C, a good thing would be to study it over CP or QP. This is a general procedure in number theory. And the interest behind the Berkovich projective line is that one can put on the same foot the non-Archimedean places and the Archimedean ones. So you can sort of treat the whole problem with a symmetrical approach. Of course, one can also study dynamics of rational maps over this type of space. And very importantly, there is the Arakelov geometry that sort of incarnate in this space and can be studied. So one can derive green functions, do potential theory over CP, and so on. So this space has driven a lot of interest in recent years for this type of reasons. Of course, why non-commutative geometry is a good tool to study that space? Well, it's for the usual reason that, well, you have this space that is has not a differential structure, but nonetheless has a lot of symmetric and sort of geometry in it that non-commutative geometry can capture. And of course, it has its relation with the number theory. So of course, we know the Bosco system that has been built to study with this approach to a group of ideals. There is a quantum symmetry of modular Hecke algebras, and actually a lot of the algebras that we're going to derive in this Berkovich space are sort of similar to these Hecke algebras. And of course, the dream would be to do a non-commutative geometry approach to Arakelov theory in this type of space, in the Berkovich space. So let's now talk briefly about the Berkovich line, give the definition. So let me recall first the definition of a non-Archimedean absolute value. So it has this, so it's a multiplicative norm with semi-norm with this non-Archimedean inequality over a field K. And so one can define a P1K over over a field, a non-Archimedean field. However, the space that one gets is totally disconnected and not locally compact. So it doesn't enjoy the usually nice property of a space. For these reasons, Berkovich has designed this, has constructed this new space that what we call the Berkovich projective line, which much nicer properties. So how to do that? So one consider the set of polynomials over this non-Archimedean field and look at the multiplicative semi-norms. And if you take the set of all such semi-norms, it defines something called the analytic spectrum or the Berkovich spectrum, which is very similar to the Gelfand one. So it's a set of all non-zero multiplicative semi-norms over a ring A. And you want the functions that define these norms to be continuous. So if you take K to be CP, for instance, then what you get is the Berkovich affine line. If you join a point at infinity, you get the Berkovich projective line. And if you look at the interior, so you remove the boundary, you get the hyperbolic line. And so the topology on this space is the usual Gelfand topology. So you want these the norms to be continuous. And what you get is the Berkovich polynomial. So this is the abstract construction. There are many different ways to define this space, but the very interesting property is that you can represent this space as a tree. It's actually a real tree, and you have a classification of points on that tree. So you have different type of points. It's called the Berkovich classification. So the type 2 points are the points in the tree where you have branching. So you have, if you consider CP to be the field, then you have a countable number of branches, at a type 2 point. The type 1 points are the points that are at infinity. So at where infinity is the distance. I haven't specified yet the distance, but these are the points on the boundary. And then you have the type 1 point, which are the points that essentially glues the type 2 points. So it's, if you want, it's the classical points on this space. And the type 4 points are degenerate points. So they end, but they are not at infinite distance from the root of the tree. Another thing that is important to notice is that the type 2 points are dense. So you have branching points and you have a dense set of such points. But it has essentially this tree representation. In addition to this, so it's a compact, of course, so it's going to be a compact set. So the projective line is going to be compact, path connected, Hausdorff. And every point we can associate a diameter to every point, which is going to be a rational number and is defined by this infimum over on the norm of the polynomial t minus a, where the norm here is the norm associated to the point x. So remember, every point on this Berkovich line is associated to a semi-norm, so we can index them by x here. And we can define a metric using this diameter. This makes this Berkovich line a metric space. And in fact, if you look at the interior, so the hyperbolic space, it's a Gromov zero hyperbolic space. So to understand the metric here, if you want, if you have, for instance, so you have this drawing here, you have a point x and a point y. Rho here is on this drawing is the root. So to compute the distance, you look at the first point, so x wedge y, where the path from the root to x and the path from the root to y are going to be different. So it's a branching point where they join together. That's the point that it's always a unique point, and we call it x wedge y. It's a property that is specific to real trees. And the Berkovich one is a representation of such tree. And this x wedge y is used to compute then the metric, the distance between x and y. So it's going to be 2 minus log p of the diameter of this point minus log of the diameter of x minus log of the diameter of y. Okay, so we have a nice space in many senses. It's compact, path connected. We have a nice metric. And of course, ideally, we would like to do geometry on that space. So this is where noncommutative geometry enters. And I'm going to start with the first, say, naive approach to construct such geometry on this Berkovich line. Something I forgot to mention. So this Berkovich line is very important, can be written as an inverse limit over finite trees. So of course, the full space is an infinite tree. But since you can write this as an inverse limit over finite trees, you can use that information to construct a spectral triple on this space. So if you consider a finite tree, any finite tree, you can take the algebra of Lipschitz continuous functions on gamma, and you take a representation which is essentially built at using the connectivity on the graphs, right? So you take this function, you can define a representation, and you can define a Dirac operator using the metric on this Berkovich space. And this is done on a finite tree, but then you have maps between finite trees using the fact that this Berkovich line can be constructed as an inverse limit. So then you can construct a direct limit of spectral triples, sort of infinite sequence of finite spectral triples.
Sorry, may I have a quick question?
Yes, sure.
So how do you understand the morphism between spectral triples?
So essentially you use, so there is a definition of morphism, maybe I should have recalled this. So you use the morphism between trees, so it's an inverse one. And basically you can define arrows that goes the other way and essentially map the algebra over gamma to the algebra over gamma prime and the representation as well. So you have a way to sort of map one representation to the other using this the induced map from the inverse limit.
Could you spend a little more time explaining this? So the V plus sim to V, what does it mean? It means that it's nearby V. What does it mean on the tree?
Yes, it's nearby. So you take V and you take all the edges that are connected to V.
Yes, yeah.
And then you sum over this connectivity.
Yes, and yes, so this is the representation of the functions. Yes. But what is the operator now?
So D here is, so 1 over, so here that's the distance. So you want to add the distance in this Dirac operator. Sure. And essentially you define this to be a diagonal one. So you 1 over rho V plus would be the eigenvalue essentially of this operator.
But what is sigma?
Oh, sigma would be a sort of Pauli matrix. So to
but
so it would be.
I'm a little bit confused. So let's see what happens in the simplest case. So if I take a graph which has say 3 outgoing edges at one vertex, what will it look like? So it will be.
So it's for each vertex you would have actually for each edges that are connected to V, you have one such matrix. So you have a direct sum for each vertex, say V1, V2, V3, and so on. Yeah. And the eigenvalue associated to one edge would be the distance between these two.
I understand, but what about the commutation between the D and the functions? How does it work?
So
you mean you have it so that the distance corresponding to D is your distance, huh? This is what you are doing.
Yes, that's what I'm doing.
So I mean the D, which has the dimension of an energy, not of a length, is constructed in such a way that when you compute the distance formula, you will get your distance. Huh? This is the idea.
Well, this will be the idea, yes.
Yeah, okay, fine. Okay, fine.
Is that okay. So you define this direct limit of spectral triples, and well, you have this inductive limit that you can construct, and in some sense, this is we would like this to capture the metric on this Berkovich line and the geometry on it. So. Of course, there are many things that you could do with this inductive limit. You would like first to construct invariant measures that are associated to this space using the usual trace of this operator. So you have this operator D, and you would like to compute these traces, and you would like to make them convergent. So you can define mu as this measure. You can define Dirichlet forms, which would lead to define a Laplace operator on these spaces. Of course, many of the usual theory on the Berkovich line, I believe, can be recovered using this sort of naive approach to construct this spectral triple over the Berkovich line. However, you would rely on this direct limit construction, which make things a little bit more subtle to construct, because you have to allow convergence of this object to be well defined, and the operator D is not immediately accessible in the sense that it is a limit of operators, and it's not clear how to derive all the usual, say, potential theory results from this operator D. I'm not saying that this is not possible. I'm just saying that this approach is maybe a little bit more difficult to continue from here.
I just
So
have one
yes,
question.
yes, sure. Yes,
Yes,
please.
I mean, is it true? So you said that it's a tree, huh? It's a tree.
Yes, it's a tree. Yes, it's a real
It's a
tree.
tree. Yeah, and it has a specific origin, if I understand well. There was
Yes,
a
yes,
yeah. But then
yes,
there is a
absolutely.
natural, sort of operator F with square one, which is coming from the which was used in the case of the groups acting on the free groups and so on. So I don't know if this will play a role, but that should
Yeah,
play a role in a way. I mean,
yes, definitely. Well, so I haven't checked special. I mean, not sure
how it relates, you mean?
if
Yes, yeah.
yes, if there's one, but so specifically to that construction, what I wanted to say is that because you rely on this direct limit, getting a clear expression on the operator that you're working with is less obvious than if you had a construction that wouldn't rely on this inverse limit. I'm not sure if I'm clear here, but that's the idea. Yeah. So maybe another approach would be to look at, so the full tree, it has a graph structure, right? So another approach could be to look at the graph C-star algebra associated to this Berkovich space. And so again, we have this this picture. As you said, you have a root, okay, and you have branching and so on. And you have these type 2 points, which are essentially giving you the branching between the points. And so one would like to associate a C-star algebra to this infinite graph. So to do that, usually what you need is an alphabet that essentially gives you coordinates on this on a graph, right? If you have a finite graph, then you have a finite alphabet. In some cases, even if you have an infinite graph, you can still work around with a finite alphabet. But here you have this infinite graph with a dense number of points. So the only way that you can do that is if you find an infinite alphabet that sort of gives you coordinates on this graph. And there is a construction that actually gives you that, and it's the following. So you take the Berkovich projective line. Yes.
Sorry, Damien. So
yeah.
I guess I don't know, but I mean, there is no obvious way to attach a group to this tree, right? I mean, this is not like Cayley graph of a group or something.
Sorry, you mean a group? What type of group are you?
Is there a group whose Cayley graph or something like that would be this this tree?
You have groups
like in the case
for
of
which the tree is this one.
Sorry,
but there is no simple group for which this would be.
Yeah,
the
I guess the question of Masoud had to do with the fact that exactly, I mean, in the case of the free group acting on the graph, I mean, if you want the spectral triple, or if you want the thing was related, in fact, to the group ring, not to the function on the tree.
Oh, I see what you're saying.
So this is what Masoud was.
Yeah, exactly.
Yeah, okay, I see what you're saying.
I mean,
but now the question is,
yes.
Yes, sorry. So now the question is, can you get so usually, I mean, the group representation, if the group is compact and so on, and you have nice properties on the group, then getting the representation and
but you see here in that case, I mean, because if it's supposed to be the projective space, then I mean there is the PGL2 group should act on this
Yes.
projective space.
So this is, yes. So PGL2 is going
So,
to
I
come
mean,
up in.
so this should be
in
the answer to the question of Masoud, and because PGL2 is very much related to the free groups. So,
yes, yes. So
then,
PGL2 is actually the,
right.
yes.
Yeah.
So
So
PGL2, yeah.
maybe there is an analog of F, of your F.
Exactly. That's what I had in
this,
mind, you know, because
so
this,
yeah, we should find it. Maybe there is
yeah,
an
we
analog
should
of
find
F
it.
because of relation between F2
Yeah,
and
exactly,
PGL2.
because
as you
this
said.
F had a, you know, fantastic
I
property,
think we should find it. Yeah, yeah.
and we
Exactly.
should find it. Yes, definitely. Yes. Okay. Sorry to interrupt you.
Yes. So no, but to continue on your remarks, so PGL2CP is the automorphism group, as you said, of this Berkovich projective line, and is going to show up at the end of my talk when we're going to look at invariant measures on that space. Yes, absolutely.
By the way, Damian, you didn't say what CP is. Maybe in words you can say once what CP is.
You mean the p-adic field?
The completion and then algebraic completion and this complex p-adic complex numbers. That's what you meant, right?
Yeah, p-adic complex. Yeah, sorry, I didn't recall that.
But that's
yes.
Fine. I mean, everybody knows, of course, but that's yeah.
Yeah, sorry. Maybe I'm.
No. I mean, that's totally fine. Sorry for interrupting. That's okay.
Yeah. Okay. So the graph system algebra over this space. So there is a way of doing that. Is that you can associate an alphabet. Well, you can construct an alphabet. If you take the rational numbers on 0, 1, you can define a set of admissible words. That is this infinite sequence of rational numbers. Here, the notation is Qi is some rational numbers. You order them, so QiL is strictly less than QiL plus 1. And the upper script K1 means that Qi is repeated Ki times in some sense. So this is a set of words, and it actually gives you, so here I'm not going into details, but there is another construction of the Berkovich line using this infinite sequence that allows you to recover this tree, and this tree will be the set of such admissible words.
But
here the choice of rational.
What is not clear in what you say is where is the prime number p now in these words and shift?
That's a good question. In fact, it's not in there. So the thing is, if you take CP, the Berkovich line over CP for any p, what you get is this tree, and you get the same tree, homomorphically speaking, if you take a different p. You see?
Wow, that's
yeah. So that's. Yeah, so that's a bit annoying because you expect, this tree to sort of distinguish between between the primes, right?
I see.
But it's not the case. It's not the case.
So because what I would have expected is that, for instance, the number of edges around some vertex is related to the number p or something like that.
No, it stays uncountable. Yeah, it stays. It stays countable. So you have a countable numbers of branching at each type 2.
Yes.
For any CP, for any p, for any prime number.
I see. But okay, then I'm a little bit confused because I would like to, if we have at the end of the day the group PGL2 of CP which is acting, then it should remember what is CP. I mean this graph. I mean
Yes, the action of the group remembers, but
I see. So the action of the
group,
group,
not the tree, not the full space. I mean.
I see. Okay, very good. Okay.
I think that the isomorphism is not natural between those trees. I mean.
I see. You mean it's just counting
It does not respect the structure. Yes. I mean, it's like
saying two Hilbert spaces are the same.
Okay, yeah, exactly. It's like the cardinality argument, essentially.
Okay,
more than that. I mean.
By the way, so the tree that I'm mentioning, it has another name. It's called the Wajewski tree, and this one is sort of it's this unique tree that you can have with a dense number of branching points and the countable branches at each of these branches. It's sort of a unique construction, and they all relate to this tree.
Okay.
So sorry, probably a follow-up question. So you said
Yes.
that this homeomorphism type of this line does not depend from the choice of P, but how about the structure of the spectral triple?
So the spectral triple depends on the metric, and the metric remembers the number P that you're taking.
Ah, okay.
So it's in the metric. Yes,
It's in the metric. Okay.
Yeah. So you have this alphabet over the rational numbers, and you can define a shift map over this. So I believe you are seeing where I'm going with this. You have right inverse to these shift maps that I call, well, the shift map is sigma, and the right inverse is sigma q. And so you can define a Boolean algebra generated by cylinder set, and this pretty much gives you a C-star algebra over P1 CP with sort of the usual, well, it's generated by projection and partial isometries with the usual relation. Okay. So of course, well, this is the abstract construction, and then to get a representation of such a C-star algebra, if you will need something called a semi-branching system. So if you consider a general measure space X mu, and you have the countable family of a map sigma I that are measurable maps, you can define a semi-branching system if these maps satisfying the following properties. So the set of ranges of this map is essentially, so if you take the union and you take the complement of the union, then it should be of measure 0. The intersection of this map should also be, of these ranges should also be 0. And the Radon-Nikodym derivative of this map should also be strictly positive. So if you have such system, which is called a semi-branching system, then you can define a representation of this C-star algebra as the following elements. So if you consider the L2 space over P1 with some measure mu, if you take an element of your alphabet Q, then you can define SQ, which is the partial isometry. And the map that takes an element SQ of your C-star algebra to this SQ extends to a star representation of your algebra. So this is sort of very similar to what is done in graph C-star algebra, except that now it's extended to this space with an infinite alphabet. You have a Kunst-Krieger relation, and you can recover the projection and so on. So this gives you another way to construct a C-star algebra over P1 without relying on this inverse limit, right? You take it as an infinite graph, and then you associate a C-star algebra to this infinite graph. So this is a different construction.
This one does not depend on
Yes.
the prime number P.
This representation does not represent. That's a good question. So the measure mu, so it's in this L2 space here. The measure mu that you pick is an invariant measure, and it's invariant under the action of the automorphism group. So, and since the automorphism group depends on CP.
No, there cannot be a measure invariant under the full automorphism group.
Not the full, sorry, not the full automorphism, but actually a Schottky subgroup of this space. So
so until we reach the group, yes, okay, fine, okay, but I mean, as such, it does not really. I mean, the choice of the measure might be, but it seems
yes, but as it is, yes, as it is, I didn't put the metric, for instance, in this construction.
Okay.
Yes. So, but I'll come back to the metric in a few minutes. I'm checking the time. Yeah. So of course now once that you have this construction, you can define operator values measure using this construction. So here is just reminding the definition of an operator value measure. So P of the full space is the identity, P of the empty space is 0, and then you have these measure-like properties that you would like to have on this projection valued measure. You can define this using on this space. So to each cylinder, you associate a projector, and this extends to a spectral measure, and you can decompose any measures on your space using this projection valued measure. And so again, you can define transfer operator, Perron-Frobenius operator out of this. And now, once you have this, you kind of say, okay, maybe we're not too far from the Laplacian using this C-star algebra. And now the idea is that, okay, you have this C-star algebra, you would like to define a graph like a Laplacian, and that's where you incorporate the metric. And now here the metric in the Laplacian depends on the prime number that you're picking. So let me be clear about this construction. This graph-like Laplacian should be very similar, if not an analog, to the graph Laplacian that is constructed by in the potential theory, people who studied potential theory on the Berkovich projecting line.
Damien, I'm sorry to interrupt you again, but
yes.
the little blue rectangle that you have put here makes me doubt that it really depends on P, because if I change P, I multiply everything by a scalar.
That is true. Yes, that is true. Yeah, I see what you're saying. Yeah, in that sense, it's. I mean, the metric. Okay. What I wanted to say is that P appears in the metric. I'm not saying that it fully, like, it would give you like a clear distinctions between the primes.
Yeah, because I mean, you know, as it's written,
Yeah.
I mean, it's just normalization where you take log P, but I mean, this is a minor normalization factor.
Yes.
So
yeah,
I really want to do something which depends on P. I mean.
Yeah. So I'm not, what I'm saying is that, okay, so if you have this graph Laplacian, you can use this to find green functions, which are related to this function that is constructing using the distance. And what I'm saying is that this is as far as I can get to capture the dependence on the prime numbers, which is not much. But when I look at what is obtained from potential theory, for instance, in the Berkovich line, that's exactly the green functions that people get usually when they do potential theory. So I sort of recover the results, but using this non-commutative approach. But in fact, it is still something, it's still an open question. I still don't know how to do better to capture the metric. It is very possible. It is very possible that here I'm showing you possible candidates for the C-star algebra. Okay, you have the first one with the graph, like, you know, with the direct limit. You have this graph C-star algebra associated to this. But it's very possible that the C-star algebra that I should consider for the Berkovich line is yet another thing.
Yeah, you see, what I really want to strengthen the actual structure that you have, and I mean, in my eyes, until it will really spit out the number P, I will be skeptical. And,
sorry, can I say one comment at this point? It seems to me by looking at this construction of the Berkovich over CP, so it's like when in geometry, locally, you construct, you should have also a reduction mod P of this construction. So what Damien is constructing is like in the Mumford curve case, is what you have as a generic fiber of a small neighborhood which contains P, but you don't go mod P. Well, if you want to have information of the number P, this construction should have a reduction mod P, and in that reduction mod P, you will have the information. This is like when you have the generation of a curve at some prime, And rather than taking the reduction at that prime, you look at the sort of what happened in a neighborhood of that prime. So you are away from the reduction in this construction.
I see.
Well, okay. I mean, I'm not quite convinced by that either, in the sense that here we are doing analysis. So the coefficients, I mean, we are taking complex valued functions in any case. So we cannot reduce mod p. But I think that what should appear, and it will probably appear soon in your talk, is the group action.
Yes.
You see, I mean,
Yes,
I really want to see the group acting, because it's there that, you know, I mean, the C-star algebra should be the C-star algebra of the group of PGL2 of the CP, you know, really. I mean,
Yes.
Okay. So let's talk about well, KMS and invariant measures.
So
oh yeah, sorry, Masoud, sorry.
No,
sorry.
that's and one more remark. I think at this point would be very interesting, as we discussed, to see this Laplacian as a square of a Dirac, and we don't know.
That's yet another. Yeah,
oh,
that's
and
yet
you don't
another.
know that. I see.
We don't
I
know
see.
that yet. Yeah, I mean
You
that.
don't know that. I see.
Yeah,
don't
that
know that.
Dirac might be
Okay.
very interesting. Actually, might be. We'll have curvature.
But you mean this is already a problem at the level of finite graphs? I mean, it's not an infinite problem.
For finite graphs, I think we had. Okay, I see. Yes. Okay, that's right.
Yeah.
That I don't know has been investigated. Okay, yeah, but I mean, in this case, I suspect that there will be some curvature term if
Okay.
you do that. Okay, but we'll see. I mean, yeah. Okay, so yeah, just
Okay, so let's move to KMS states and invariant measures. So of course now this is sort of a third construction. Okay, it's a third C-star algebra candidate, maybe the good one in the sense that we consider for the C-star algebra. So here I'm just recalling briefly what a C-star dynamical system is. You take a C-star algebra, and then you have one parameter automorphism acting on this C-star algebra, and you consider a state of this C-star algebra. So this is just a brief reminder. And then, of course, KMS states are states of particular interest because they have invariance properties, symmetries properties under the action of this dynamical system. And so, okay, before talking about what happens in the Berkovich on the Berkovich projective line, maybe we could recall what happens on the disk, right? On the disk, you have the Poisson kernel, and then you have harmonic measures that you can define on the disk, and these harmonic measures they are related to something called the Busemann function, which is to say, if you take the so d nu dx, sorry, d nu x and d nu y, if you take this quotient, you get the exponential of this Busemann function. And you can construct an invariant measure on the disk, which is called the Patterson-Sullivan measure. Okay, so this is known on the disk, and the important kernel on the disk is the Poisson kernel. Now, if you go to the Berkovich projective line, what replaces the Poisson kernel is this, maybe I should have highlighted this, is this log of delta, where delta here is just related to the diameter of a point, right? This replaces the kernel, the Poisson kernel, in the case of the Berkovich projective line. Okay, so you can define this Busemann function on a tree. Okay, so you can define this on the Berkovich projective line. So you know that there exists a Patterson-Sullivan measure on the Berkovich projective line using usual Gromov hyperbolic theory on trees, right? So you can define this Busemann function. So to do that on the Berkovich projective line, so here I remind that PGL2CP is the automorphism group of the Berkovich projective line, and if you
no. Here, stop here.
Yes.
Stop here. I mean, we are at a key level. Yeah, because you were telling that the Berkovich projective line, when you consider it as a tree, doesn't see the number p. So this means that now you are enriching the structure because you are in order to get the action of PGL2, now you have a rigid structure. So this is the
Yes.
structure I'm interested in. I am interested in the action of PGL2CP on these three, okay?
Yeah. Yeah.
And
The thing is, well, yeah,
yes.
PGL2CP is too big to, you know, to get
No,
to get this action.
no, it's not too big for the F. Not for, of course, it's too big for the
Okay.
Dirac, but it's not too big
Okay.
for the for the sign of Dirac. And because
Okay,
the
I
sign
see.
of Dirac allows to have infinite groups which are almost commuting with it. And so this
Okay.
should be
Because well, okay, maybe I got scared when I approached the problem because PGL2CP was
no. I mean, this is
thing.
where the treasure. There is a treasure waiting for
Okay.
you.
Okay, so okay, well then maybe I have to dive into the wild here. So I single
Can
out,
I
you know,
add one thing further, because in this discussion of, for what I know about the Schottky curves, for example, on local fields. So this is a construction over CP which allow you to recover the information at P. This is it would provide a way not to reduce mod P, but in fact to recast. This is part of certain construction in algebraic geometry in nodge theory, that they want to recast on the field for, in this case, CP, certain aspect of the geometry that has to do at P. And so this is known that there is this construction at the boundary, which means on CP,
yes,
that is able to
yes,
reconstruct the information at P. And this is the
absolutely.
very same process going on.
It's the same process. Yes, exactly. Yeah. That's it. Thank you. Yeah. So you know, so you guess actually what's coming. You know, then from the next slide. I'm just gonna state it. So you know, you single out this Schottky subgroup and you consider its limit set, and then you take the cross product between, you know, the continuous function on this limit set and this Schottky subgroup that you've chosen. And then you have one parameter automorphism. This is the usual construction, right? So, and it defines you a C-star dynamical system. And then from the set of KMS states of this C-star dynamical system, you can reconstruct this Patterson-Sullivan measure out of this. So this is yet another construction, another C-star algebra that gives you information. But as you mentioned, and as I said earlier, I wasn't happy with any of these of this construction for different reasons. But the reason is that, in fact, one of them was we did not capture, you know, clearly the difference between, you know, two projective spaces when we change the prime number P, and for the fact also that it's not clear what should be the Dirac operator. Well, maybe in this specific one, the Dirac operator then is associated to this one parameter automorphism group, and it has as eigenvalues this Busemann function. But this is a very particular, and it depends on the choice of Schottky, you know, group that you're taking, I'm assuming here. So many remains to be done. So of course there are many objectives. You know, one of the first long-term goal that we set is to recast Arakelov theory, but, you know, with this non-commutative geometry approach, you know, to find green functions and Arakelov green functions using this, which is already something that is done using potential theory, by the way. So they re-derived, you know, this green function and so on, and they have, you know, sort of all this construction running. But I haven't seen them, you know, talking about, you know, the difference between the prime numbers. This is not something I've seen.
Jonathan is
of course,
there is
Jonathan
a
is
question.
asking a question. Jonathan Rosenberg
sorry.
is asking, when did you put in the subgroup gamma? Did you introduce a subgroup gamma?
Yes, gamma.
Yeah, exactly.
Yes, it's a Schottky subgroup.
Yes, and then this means that the construction will depend on this choice of gamma, of course.
Of course.
Yeah.
Yes.
Okay.
Yes. which makes it unpleasant, right? You would like to have something that does not depend on such choice.
No, but I mean,
Um,
what I would easily conjecture is that in fact not the spectral triple, but the quantized calculus, if you want, with the operator F, with the Fredholm module, that will not depend
Mhm.
on the choice.
Yeah.
I mean, there should
Okay.
be a universal one, like the one which was used, for instance, in the case of the free group.
Yeah.
It seems really to be there and waiting to be used, you know, really. Because
Okay.
you have in the tree, you have a specific origin on top of that. And this was the only thing that was needed in order to define it. So, you know, it seems to be completely clear.
The origin is the Gauss point, right? I mean,
Yeah,
Yeah,
it's the
the
Gauss
origin
point.
is the Gauss point.
Yeah.
And the operator F was defined
Yeah.
using the origin. That was it.
Yeah. So it's yeah, I mean, it reminds you your paper, of course. Yeah. Your F, yeah. That's very, very good point. Yeah.
Of course, and you can consider, you know, the Berkovich space over Z, right? You can do that as well, and that would be interesting as well to study that space instead of the CPs. Yeah, and so some other possibilities, you know, matrix models, you know, non-commutative. You know, ideally, I would like to have, you know, a Laplace operator that can be written in this following form, which easily lead then to the Dirac operator. Yeah, so many remain to be done. Yeah, that's a take-home message, I guess, on this Berkovich project. Okay, thank you for your attention, and thank you for your question.
Yes.
Yeah, thank you very much. Yeah.
Yeah, I have a number of specific comments. One comment is that I presume that the action on the Schottky, I mean, on this boundary, is amenable. You see, I mean, the group PGL2, of course, should not be, I mean, because it's like a free group. But
No, it's
when you look at the action on the boundary, it should be amenable and so on. And indeed, I mean, you know, the issue there is more, okay, I mean, we know very well that you know, like the theorem of Bowen and all that, they can be reformulated in terms of KMS on the boundary of the hyperbolic space. But here the issue is more, you know, what non-commutative geometry can bring, which is totally inaccessible otherwise. And that should come from this Fredholm module on the tree. And implementing things like the non-existence of projections in groups which are involved around and so on, in the C-star algebra, in the reduced C-star algebra of groups which are involved around there. So I think, you know, this is, I don't know, I mean, this is an open question, but I think it's quite interesting to do that.
Yes, definitely.
Yeah. Yes. That seems to be central question, actually.
It is.
Yes.
Yes. So I'm glad you gave this talk.
Yes. Yeah, because I am fascinated by the if you want, the coherence between these three and actually I mean, what we know about C-star algebras of trees and so on, of groups acting on trees and so on. So there seems to be a very, very strong interplay.
Yes.
Now, but if you want to get Dirac operators and all that, then of course, I mean, the group has to be reduced considerably.
Yes.
It cannot be
That's
because
the thing.
Yeah. No, I think Fredholm module is the
it's
should
the
be-
right thing.
should be the
Otherwise, it will
focus
be
now.
only theta summable. Otherwise, you know, you will not get a finite dimensional spectral triple. It's impossible. There is an abstraction to do that. So, I mean, you'll get something which is theta summable, but you won't get something which is finitely summable. I mean, this is for sure.
Would be great, in fact.
Yeah. So anyway, thanks a lot, Damien, for this great talk. I mean, you know.
Thank you for all your comments and your questions.
Are there any other questions or comments? I mean, Jean made me the host because he had to teach.
Okay.
So he gave me the.
Yeah, well, usually Adam has questions. Adam, do you have some questions?
Yeah, Adam has questions.
No, sorry, I'm thinking that I'm happy. Thank you.
Okay.
Beautiful talk.
Thank you.
Yeah.
Thank you.
Okay.
Any other questions or comments? Okay. Well, looks like there are none. Well, thank you so much for all
Thank
the
you.
questions.
Thank
Yeah,
you,
Thank you. Thank you, everyone.
Yeah.
Thank you. Thank you for your
It
patience.
was
and your
great,
questions.
and we will meet again sometime. Yeah.